Hello everyone, I hope you're all doing well today. Welcome to your applied mechanics lesson. On today's video or on this lesson, we will be dealing with vectors. So normally a question would ask you to calculate the magnitude as well as the direction of a resultant vector that is formed. And on screen, you'll see we have a diagram on here. It has force 1 of magnitude 200 newtons at 30 degrees from the horizontal. And then we have a second line F2 that has a magnitude 300 newtons. It looks like it is 45 degrees from the horizontal, but remember that we have to use a neutral axis. So you would remember that this is your 0 or 360 line. Then that would be your 90-degree line, that would be your 180 line, and this would be your 270 line, then back to 360. Okay, so in as much as your F2, it's easy to say it is at a 45 degree from the horizontal, but for purposes of our vectors, you need to make sure that you are always taking your angles referenced from your 0 or 360 line. Okay, then next we're gonna jump into the steps we follow, and this is essentially how we go about solving when you're asked to calculate the magnitude and direction of the resultant. Essentially, we're trying to figure out, with force 1 pulling away from the center on here and force 2 pulling away as well, what would be the resultant? How would this body end up acting or reacting to those two forces that are now acting on it? Okay, so you know that I like normally pointing out steps. So step 1, we're going to determine our components. Then step 2, we're essentially gonna sum our components. Then step 3, then we are gonna calculate our resultant force. Okay, I'm just gonna minimize that a little bit to give us a little bit of space. Right, so step 1, we are now getting our components. Okay, so I'm just gonna go back to the same diagram. Just zoom it out a little bit. Okay, great. So we have force 1, force 2 on there. And you would remember, just a recap, how we go about finding our components. We use our SOHCAHTOA. I don't even know if the way I pronounce it is how everyone else is pronouncing it. But anyway, that's how I go about it. And the main idea here is that if you have a triangle on here with angle theta, and this would be your x, your y, and let's say this is your line, let's say it's your force R or your line R. The idea on here is that you would try to essentially express your y and your x in terms of your angle theta. So you would look at what you have and what you're trying to get. For instance, if you're trying to get the magnitude of your line Y or the size of the force that is acting on line Y, essentially this would be opposite to your angle, and it kind of directs which formula you'll be using. Then similarly, if you'll be using your X, which is adjacent to your angle, it directs that you will be using your cosine, right? So if you said sine of theta, it would be your opposite over your hypotenuse, right? And our opposite in this instance is y. Our hypotenuse would be that r that we are trying to solve for. Then when you cross multiply, essentially you're able to express your I in, no. He's a lie, she's lying. Sorry about that. Essentially you're able to express your y in terms of your r sine theta, because at the end of the day, you are trying to find an expression that helps you solve for the unknown while you are working with what you have. Okay, similarly, if you are now considering x, you would say your cos of theta would be your adjacent over your hypotenuse, right? And in this instance, your adjacent would be your x, hypotenuse would be your r, and if you cross multiply, your x would then give you r, cos of theta. Then essentially you've then expressed that. So remember that normally when you are dealing with a slanted line or a line that is at a specific angle, normally you would have whatever diagram and all you have is this line, right? And essentially we come up with components to try and solve for that perpendicular and parallel, which would be the y and the x. The y and x are normally imaginary lines. You essentially plant them there as a way to represent what a full triangle would look like. Okay, then obviously this would represent your x, which would be your r cos of theta. Then this would represent your y, which is your r sine of theta. Okay, now we're going back to our main diagram. I hope this part makes sense. Then we're going back here to our main diagram, right? So remember, everything is imaginary. You can plug and play it on screen, or you can decide to separate it, right? It just depends how much space you have and how neatly you want your work to be. So you plug in your imaginary lines on there. Plug in imaginary lines on there. I just hope we'll have enough space. Okay, so when you look at this, essentially it represents y, which would be here if you were formulating a full triangle. Then this represents your x, which would represent the horizontal line as well. Similarly to here, you have your x and you have your y as well. Okay, so we'll just call that one y1, x1, then we'll call this y2, x2. Okay, then we can just make some space on here so we can show how we will be solving for those components. All right, then we'll say you can choose whether you want to start from scratch with the SOHCAHTOA, but we already know by looking at this that your x1 on here, this essentially will be your f1 cos of 30 degrees. But for purposes of everything being orderly and neat, let's work it out on here. Remember that we have our SOHCAHTOA, and we've already determined which side allows us to use the sine and which side allows us to use the cosine. Okay, so we'll start with our y1. Okay, we'll say sine of 30 degrees. I'm considering this first portion will be opposite over hypotenuse. Our opposite would be y1. Our hypotenuse is our f1, right? That's the force that is known and we're essentially using to calculate on here. Then by cross multiplying, we end up with y1 is equals to f1 sine of 30. All right, but f1 has a value. F1 has a value of 200. So we can plug and play on there. Then our y1 would be 200 sine of 30. It gives us 100 newtons. Okay, that's the first portion. Then now we want to get the value of x. Right, I hope we're still following. Let me just put it on here. Then now we say cosine of 30. It's not theta anymore because we know the value. Cosine of 30 is your adjacent over your hypotenuse. Our adjacent is our x1. Our hypotenuse is f1. Then cross multiplication, x1 is your f1 cos of 30. But we know the value for f1, it's 200. 200 cos of 30. And you plug that into your calculator and you get 173.205 newtons. Okay. Then we're moving on to the second portion on here, right? I'm just gonna erase these because we get it by now. We get it. Okay, so this second portion we have an angle of 45 from the negative side. And remember what I said about using your angle from the 0 point. Okay, so if you did 180 minus 45, essentially it will tell us the angle that we are meant to use over there. Main reason being we are using our angle from the 0 line, or from the 0,360 point. That's our reference points. Okay, so next, now we're trying to get components for the other line. Okay, then y2, let's get it. Okay, so essentially what it looks like would be, remember it's the second line, we have that 135 on there. Okay, from the reference point, don't get confused. Okay, the only difference here, if you will be using it from this side, if you will be using it from this direction, remember to include the negative direction. Okay, remember to include the negative because it's from the negative side. But anyway, then we're moving on. Then we're going to start off with our sine. But we know the value of our f2. F2 is 300. And you just plug and play. Two 212.132 newtons. Then similarly, we're getting 2. Okay, I hope this part makes sense. I really hope it makes sense. Okay, so I was saying we adopt this method because it's easier to remember that you're using the 0 or 360 line as your reference point. But if you prefer to use the 180 line as your reference point, you just need to remember that it is negative coming from the left. Okay, it's just that the only problem you may encounter there is that you need to remember where to apply the negative. So if you decided that you wanted to use the 45 degree instead of the 135, then essentially we have that. That's the 45. That's the 135, right? Okay, they look weird, but anyway. And if you decided that you will be using this as your reference point, you just need to remember that when you're carrying out the y component, so if you'd said sine 45 is your opposite over your hypotenuse, right? And your opposite would be your y2, your hypotenuse would be your f2, okay? Then on here, it doesn't change much. Your y2 will be f2 sine 45, okay? Then you would do 300 sine 45, you get the same value, literally the same value, okay? You'd get 212.132, and it's positive because when you look at the quadrant on here, on this side y is positive, but on this side x is the one that's negative. Okay, so that would be fine. The problem would then arise when you need to carry out your cosine. So cos of 45 would be your adjacent, over your hypotenuse, which would be negative x2 over your f2. Negative x2 is your f2 cos of 45. Okay? Negative x2 would give you a minus, no, it's still positive when you plug it into the calculator like that. So 212.132 newtons. But because we know that it needs to be negative because of its position, then you would essentially multiply both sides by a -1 or carry out whatever maths you need to carry out. But essentially you would need to make sure that your x2 is a negative value, 132 newtons. Okay? I hope this makes sense. I hope it makes sense. So the easiest way to go about it, or a way in which doesn't require you to remember the signs that we needed to switch around on here, is by simply using the angle that you find as a reference point from your 0 or 360 line. If you have any questions, let me know in the comment section or however else you can get hold of me. I really hope this makes sense. Okay? Then the next part, remember this part was just about doing the components. So now we have the components. Step 2, we are essentially going to sum them up, okay? So now we just need to express them properly. We have now calculated our forces, okay? So we have our y1, y2, we have our x1 and our x2, all right? Then we can just plug them back into the equation, all right? So from what we calculated on here, it says our F1 is, start with the X, 173.205, that's our constant, plus 100, that's our constant. Okay, that's just how you would express it. So this would stand for whatever is on your x-axis, this stands for whatever is on your y-axis. But I think to make it a little easier so it doesn't get confusing, we can use x and y still. So 173.205x plus 100y. Okay, just so it makes a bit more sense. Then from what we calculated on here, it tells us that our F2 will be our negative 212.132x plus 212.132y. Okay? Then essentially we're expressing them in this way because those two forces work together to eventually give you a resultant, right? Then you would remember step 2, we're essentially going to add F1 and F2. Okay, so our resultant force is your F1 plus F2. Our F1 is 173.205, 173.205x plus 100y. Okay, that's our F1. Then our F2 was negative 212.132x plus, this is a plus, I don't know why it's a negative, it's meant to be a plus, plus 212.132y. Okay, then next what I normally do, I just group them together, essentially group the x's together and group the y's together. So our x's, we have 173.205, and then we have minus 212.132. Those are the x's. Then plus the y's, we have 100y plus 212.132. Okay, this y can just put it outside so it looks a bit uniform. Okay, I hope we're still together. Then 173.205 minus 212.132. This gives me a negative 38.927x. 100 plus 212.132 plus 312.132y. Okay, you cannot simplify it beyond this point. So essentially, when they ask for the magnitude and the direction of the resultant, then now we know that it is your minus 38.927x plus your 312.1321. Okay, so now we've calculated the magnitude, right? I think I'll do a part 2 where we are focusing on calculating the direction of the specific vector force. All right, cheerio.